Dear students, welcome back to the lecture series on statistical thermodynamics. In the previous video, we have seen how to express internal energy in terms of partition function. This video is a continuation on expressing different thermodynamic properties in terms of partition function. In this video, we will see how to express thermodynamic properties such as entropy, enthalpy, heat capacity, pressure, work function and Gibbs free energy in terms of partition function. First, we will see the relation between entropy and partition function. So starting from the general equation for Maxwell-Boltzmann statistics, W equals n factorial by pi I ni factorial. Take log and apply Stirling's approximation. So we get log W equals n log n minus summation ni log ni. Let that be equation 1. Now according to the Boltzmann statistics, ni equals n by q gi e raised to minus epsilon I by kt, where q is a partition function and gi is the degeneracy of the ith energy level. And if gi equals 1, then we have ni equals n by q e raised to minus epsilon I by kt. Now apply log. So log ni equals log n minus epsilon I by kt minus log q. Let that be equation 2. So now we got a value for log ni. Now substitute this value in equation 1. So that we get log w equals n log n minus summation ni, and instead of log ni we can write log n minus epsilon I by kt minus log q. So this on rearranging we get n log n minus, so here we have summation ni log n where summation ni is capital N, so here minus n log n plus summation ni epsilon by kt. So summation ni epsilon I is the total energy, which is the internal energy U. So here U by kt plus again here we have summation ni log q, which can be written as n log q. So finally we get log W equals n log q plus U by kt. Now from the third law of thermodynamics, we have the Boltzmann equation defining entropy as S equals K log W, where K is a Boltzmann constant and W is a thermodynamic probability. So in this equation, instead of log W, we can write n log Q plus U by kt. Therefore, we can write S equals K n log Q plus U by T. We have already derived the relation between internal energy and partition function. So we have U equals nkt square dou log Q by dou T at constant V. So substituting the value of internal energy in terms of partition function, we get S equals Kn log Q plus nkt square dou log Q by dou T at constant V divided by T. Finally, we arrive at the equation for entropy in terms of partition function as S equals Kn log Q plus nkt dou log Q by dou T at constant V. This is the expression for entropy in terms of partition function. So we have derived the expressions for internal energy and entropy in terms of partition function. Similarly, we can also find out the expressions for other thermodynamic properties such as heat capacity, Gibbs free energy, work function, enthalpy, etc. in terms of partition function. So let's see one by one. Heat capacity at constant volume, that is CV, which is defined as dou U by dou T at constant V, where U is the internal energy. We have already derived the expression for internal energy, which is nkt square dou log Q by dou T at constant V. So substituting for U here, we have CV equals dou by dou T of nkt square dou log Q by dou T at constant V. Similarly, we can also find out the expression for work function. Work function is defined by A equals U minus Ts, where U is the internal energy and S is the entropy. So first write the value for U. We have also find out the expression for entropy. So write that also. That is nkt square dou log Q by dou T at constant V minus T into the expression for entropy, that is Kn log Q plus nkt dou log Q by dou T at constant V. So it is equal to minus nkt log Q. Similarly, we can also find out the expression for pressure. From Maxwell's relation, we have dA equals minus PdV minus SdT, or we can write dou A by dou V at constant T equals minus P. If the temperature is constant, then this term will be 0 because Tt equals 0, so this term is 0, or we can write dou A by dou V at constant T equals minus P. That is equal to dou by dou V of, write the value for A, that is minus nkt log Q. Or we can write the expression for pressure as nkt by Q, dou Q by dou V at constant T. Similarly, we can also find out the expression for enthalpy. Enthalpy is defined as H equals U plus PV. Substitute the values for internal energy and pressure, and we get H equals nkt into T dou log Q by dou T at constant V plus V into dou log Q by dou V at constant T. If enthalpy is known, we can also find out the expression for heat capacity, Cp, which is defined as dou H by dou T at constant P. So substitute the value for H, that is dou by dou T of nkt T dou log Q by dou T at constant V plus V into dou log Q by dou V at constant T at constant P. Now the last is the Gibbs free energy, which is defined as G equals H minus Ts. So merely substituting the values for enthalpy and entropy, we get G equals nkt into V dou log Q by dou V at constant T minus log Q. So in this way, we can express any thermodynamic property in terms of partition function.